We're going to introduce one more test for the convergence of series, remembering that the ratio test that we learned the other day is going to end up being our primary test. This test is called the integral test for series. And the way it works is this. If we have an, which is a sequence, if we can express that an as some function of n or a function of x, an example would be this. We could say that an is the harmonic sequence, 1 over n, and then we can say express that same an as a function of x, as 1 over x. So what we're doing is converting the sequence into a function. And what we're going to then do with this function is we're going to say that these things behave, these two, the sequence and the function behave similarly. And if we take the integral, or the area under the f function, and it converges, we would then make the conclusion that an must also converge. Okay, the series using an must also converge. If the area underneath the f function becomes infinite or diverges, then we can say that the sum of the an terms also diverges. And again, the reason is because although they're not the same thing, the an is a discrete function and the x function is a continuous function, we can say that they behave similarly enough that the way one behaves, the other will follow. So here is the example. We have our harmonic series, 1 over n, and we're going to overlay that. On top of that, we're going to overlay y equals 1 over x. Okay, so y equals 1 over x is that continuous function in red, and the harmonic series is the sum of those rectangles in green. And what we can do is we can check to see if the area underneath that red function, we can integrate to do that. We can check to see if that area if it is convergent or has a finite sum. We're going to say that the 1 over n also has a finite sum. So we're going to check it this way. So we're just going to find this area. So the area from 1 all the way to infinity. So this is an improper integral. So we're going to set this up as an improper integral. So the area is equal to the limit as the endpoint a goes to infinity from 1 to a of 1 over x dx. Okay, so we're going to calculate that area. The limit as a goes to infinity, and the integral of this will be log of x, log x, and our bounds are going to be from 1 to a, which goes to infinity. Evaluating this area, we're just going to plug this in. So we're going to end up with the limit as a approaches infinity of log a minus log 1, which is 0. Okay, and then we're going to let a go to infinity. So we end up with log of infinity minus 0. Well, although log is going to make numbers smaller, and log is weak, log infinity is still infinity. So we're going to say that the area is infinite. So if the area underneath the 1 over x function is infinite, then the sum of the series is also infinite. Okay, so this idea of how one behaves, we can translate that behavior onto the other, although they are different. We're going to say that if the area underneath the curve that mimics 1 over n is divergent, we know that 1 over n is also divergent. Now, we've already established that the harmonic series is divergent, but this is just another way we can test it. Okay? And again, it's important to recognize that we're not saying that they are the same thing, so that the sum under the integral is not the same as the sum of the sequence, because we can see that there's a mismatch of area. But what we're saying is that if one behaves as a diverging area or diverging sequence, we know the other must follow that way. And so if we can integrate, we can test by integrating and finding areas under the curve from some point to infinity. So this integral test represents a situation where we can use a continuous function to analyze a discrete series. It's because of their similar behavior. And again, we want to make sure that we know that they are not the sum of the series is not equal to the area under the curve. It just behaves that way. Okay, so we're not claiming this. We're not claiming that it is equal, okay, to the area under the curve. We're just saying that the behavior is the same. If one converges, the other converges. If one diverges, the other diverges.